All right, so let's continue now with the next section in the overview slides, and then we will do the quiz in about half an hour or so. So if you recall, so up to this point, we've really talked largely about basic abstract data type mechanisms in C++, things like classes, methods, constructors, accessors, manipulators, all these other kinds of things. And then we spent some time talking about exception handling, handling errors. There was an interesting question on the Piazza about catch and throw versus, or try and catch versus throw. Throw is how you communicate from one level of abstraction that something's gone wrong that you don't know how to deal with, like someone passed you an invalid index that you don't know what to do with, and you're like, hey, I don't know what to do. I'm going to throw an out-of-range exception or something. That's the throwing part. That's when you detect something, and you raise that up to somebody. You don't know who. You don't know who's going to handle it. And whoever handles it, which could be various levels up the stack of activation records, of runtime stack, that's where the try-catches come in. So try-catch is how you handle. Throw is how you raise exceptions. And it's like, kind of like a game of football. You're detecting something, and you're lobbing the ball, and it's going to go someplace, and someone hopefully will catch it. And if they don't catch it, your program will terminate at the top with an unhandled exception error or something like that. So what we're going to do now is we're going to talk about another paradigm of programming with C++ called generic programming. And the main driving feature in generic programming is the template or parameterized type. It's funny, there's all these different terms for these things. Template, parameterized type, Java calls them generics, Ada called them generics. Generic programming is a paradigm of programming that in C++ is implemented with templates and parameterized types, blah, blah, blah. Here's an example of the stack implemented as a template. Now, there's lots of interesting things that we can do with templates. We're going to keep it easy and simple right now. But basically, all we're doing in this particular example is a little syntactic sugar. Rather than saying just class stack, open, paren, or open curly brace, blah, blah, blah. Now we're going to say template less than type name t greater than class stack. And t in this case is just a placeholder for the formal parameter, or the actual parameter that will be passed in as a replacement for the formal parameter, which is t. So it's basically what we're trying to do is we're trying to generalize over types handled by this particular abstract data type, which in this case is a stack, but it could be anything. A couple things. In older C++ code, you will sometimes see the word class appear where the word type name appears now. There is no semantic difference between the two. It has to do with the fact when C++ was first developed back in the early 80s, there was an attempt to try to have as few new keywords added to the language as possible, because every time you added a new keyword, you'd break existing code that used that word. And so at one point, the C++ Standards Committee decided that if you wanted to propose a new keyword as a member of the Standards Committee, you had to volunteer to give up one of your bodily organs, like your appendix, or your spleen or something like that, or your gallbladder. So they were trying to keep the keywords down. Eventually people said, using class is confusing because templates can be either built-in types like int or double or float, or user-defined types like string or something. And using class seemed to imply that you could only use user-defined types, not built-in types. So for various other reasons, someone made the sacrifice and donated a body part, and they added the keyword type name to the C++ language. And so henceforth, after that, they used type name in various places, some of which we'll see later. And then they also said, if you want to use type name instead of class, that's fine. I typically write with type name. I find it more explanatory. It's a type name. You could replace this with a built-in type, a user-defined type, as long as it's the name of a type. So that's the CliffNote version history of type name. You can see, pretty much aside from that, it's more or less the same as before, the only real difference being that we've added a scoped array here, as opposed to just using a naked pointer. And we also added our swap method to do the exception handling stuff that we talked about before. That's the only real difference. But aside from that, we made it a template. Now, there's a bunch of implications of making things templates, and we'll talk more about that as we get a little further along. One of the implications of using a template is when you start to define the actual implementations of the methods, two things need to happen. If you define the implementations of the methods outside of the class definition itself, like in a .cpp file, you have to use this somewhat cluttered-looking syntax. And that's confusing, and inevitably you will make mistakes, which is why we typically give you shells to make your life easier. But eventually you'll have to learn how to do that yourself. So you can see here, like the constructor of this thing is now, template type name T, stack less than T greater than, colon, colon, stack, and so on and so forth. So you can kind of see that there's been some changes to this thing. And so that's syntactic sugar, just to say this is part of the template class. It's not just a regular class, it's a template class. That's one thing to know. The second thing, and a bit more confusing thing, more important thing to know, is that when you use templates on 99.99% of C++ compilers, you have to include the source code for the implementations with the header file. And there's two ways to do that. One is to define the implementations of the methods in the header file itself, inside where you define those things. Basically put them as literally as inline functions defined here. That's kind of the way Java works, if you think about it. Java, when you define a method, it goes right in the class. Or you can stick it in a separate file, like a .cpp file, but then you have to include the .cpp file in your header file. And so when you start taking a look at some of the shells coming later, I think for assignment 2, where we deal with templates and parameterized types, you'll see that we include the .cpp file, which at first seems a little weird, but when you deal with templates, that's what you got to do. And you could also, of course, put it in a file with something other than CPP, but this is just a convention that most people follow. Yes, sir?
Does that mean that if somebody includes the .h, they're also by extension including the .cpp?
So the question was, doesn't that mean that if you include the .h, you're also including the .cpp? Absolutely. That's exactly what it means. So that has several implications, one of which is that in older compilers, this is not really a problem anymore, but back in the bad old days, template compilation time took forever because you had to include the header and the source code. It took a long time. That's been long since cleaned up. But more importantly, at least for some environments, is unless you're doing open source software and you want everybody to see your code, then when you use templates now, everybody sees your code. So you have to decide if that's OK. Obviously, if you're making open source software, that's fine. If you're not, then you have to sort of think of some other things. Yeah?
At least in Visual Studio, you couldn't actually, hashtag include .cpp in the H file, but you couldn't actually include it in the project.
Right.
Otherwise, everything would bonkers.
Yep, great point. So here's the observation. In Visual Studio, in Visual Studio, much like any IDE, or Makefile for that matter, you have to describe which files you want to have compiled. And if you put the stuff in the project file, then things would get confused. So what you typically do is you don't put the .cpp file in the project file, you just include it through another header file, and then it works fine. So it's basically like an inline file. Yeah, very good point. Yeah?
If you include the .cpp in the .h, like at the end of your definitions, and you say it's technically inlined, does that affect the functions in the same way that inlining other functions is, like we discussed in the previous lecture?
So the question is, what's the implication on inlining versus non-inlining of functions? It's really up to the compiler to figure out how all that stuff gets worked. Okay. And the main thing to remember with templates is when a compiler sees a template, it doesn't generate any code. Instead, it stashes that template away someplace in a library, a repository, a file system directory, or a folder, or something like that. And then later, when you go to instantiate the template, you say like stack of int, or stack of double, or stack of employee record, or whatnot. Then it goes through and it looks to see which methods you actually use from that template. And then, and only then, will it compile those methods for that particular type. And that's the object file that gets linked in with your program. So that the behavior is a little bit different with templates than with regular classes. Because when the compiler sees a regular class, it goes ahead and compiles the whole class into a .obj file, or a .o file, or shared object file, or .so file, or whatever your compiler does on your platform. And those things sit off by themselves, but they're all compiled in there. And then when you link, you'll get the things linked in. But a template is different. It doesn't actually generate code when the compiler sees it. It just parses it, maybe does error checking, maybe not at compilation time. When it does instantiation, then for sure it'll do error checking, and then it'll also go ahead and generate the minimum amount of code that you need. Now, you don't have to really know that at some level to be an effective C++ compiler. That should all happen by magic. but it's kind of cool to understand these things. And it also helps you with some of the weird errors you might get in some circumstances. And we'll see later when we get further into templates that there are some really weird errors. And modern compilers are a lot better than they used to be about giving you sensible error messages, but it often looks like line noise when it comes out. Okay, aside from that, most of this is the same as before. Because I used a scoped array, the destructor becomes a no-op. As somebody pointed out before, we could just leave it out altogether. Wouldn't cause any problems. I'm just leaving it here to make it a no-op, just to show you, remind myself to tell you that. Push and pop, the behavior is the same. Here is the great thing about templates. Templates work best when the algorithms that you write for your data structures, or your containers, to use an STL-like word, are orthogonal, which is just a fancy way of saying independent, of the types of the data that they work on. So if you think about what does it mean to push or pop something on a stack, that's really independent of whether it's a stack of int, or a stack of float, or a stack of employee record, or a stack of double, or a stack of activation records, or a stack of whatever. The logic is exactly the same, and that's what templates are so good for. They're doing substitution of these formal parameters of type name T or whatever with the actual parameters passed in when you instantiate them. And we'll see an example in a second of how to instantiate this stuff. And here are the examples. So as you can see in this particular situation, we're going to go ahead and have a stack of ints, a stack of floats, a stack of pointers to activation records, right? So you can nest this stuff in all kinds of crazy ways. And then we can do various operations, pushing and popping and so on and so forth. So templates are really pretty much orthogonal to most other things in C++. Access control, specifiers, allocation and deallocation of memory, exception handling, blah, blah, blah. They're just generalizing over the type. Now, it turns out that there's a lot more to templates than that. There's also ways of generalizing over values. There's ways of generalizing over function pointers and so on and so forth. But the best way to think of them for the point of view of what we're discussing at the moment is a generalization over type. And we'll see some other examples. As we start getting into STL, you see the whole essence of STL is to separate, to use patterns to separate out the containers, which are the data structures, like a stack or a queue or a map or a vector or whatnot, from the algorithms, like equal, fill, and other kinds of things. Separating those two things out, sort would be another algorithm. And the way in which you combine the algorithms with the containers is through the use of something called iterators. And there's some really cool patterns that apply here. The iterator pattern, of course, various strategy patterns, various factory patterns. More advanced uses would use things like bridge patterns. By the time we get done with the class, you'll have experience with all that kind of stuff. So I'll unfold that gradually as we go. Any questions about any of that?
This is purely the code on the slide there. You may bring this up in the next slide. And I'm referring to something that was taught to us in NCS 201.
Sure.
So you can respond to it as you wish. The S3.pop SAR line, that would be, I assume, popping the new activation record off, or the new stack of activation records off of S3 stack, and then storing it in SAR.
Yes, that's correct.
Okay. So in CS201, we were told that generally we should use an operation that we call top to retrieve that data, and then top would simply be to remove the data from the stack.
Great point.
In that case, it's not separated. So I guess what is the response to that?
I'll repeat the question in a second. Okay, that's an excellent point. In fact, you'll notice here that, oh, this is great. Beware this implementation. So why are we being wary of this? Let me tell you about that. Very, very, very important point. If you take a look at the, put that in here too. So if you take a look at the C++ stack, just to use an example, in the C++ stack, pop doesn't return a value, and top returns a value but doesn't change the stack. So they're two separate operations. Our implementation here tries to be clever and tries to do two things at once, right? It tries to remove something and it tries to return something. And the observation, which is a very good one, is don't do this. So this is like, what not to do, what not to wear. So does anybody, do you remember why you had that recommendation in 201? Yeah.
So I guess the distinction is between a mutator and an accessor. And generally, so mutators actually change the stack data type, and accessors just take data out of it, so they don't actually change it.
Yep.
You use like the const keyword to know that they don't change the actual data type. And if you use pop to both remove them from the stack and also access data to it, using both mutator and accessor at once, and it tends to be very confusing to have both of those together at once.
So you're right. Well, actually, you could argue it's not confusing, but there's another more deep, more profound reason why we don't want to do that. Yeah.
Sometimes you just want to examine the top element.
Oh yeah, and we have a top. So absolutely right. You don't always want to pop. So that's right. Does anybody know why we don't want to combine the two though? What's the semantic reason why it's a bad idea? Well, top will do that for us. So we have a top.
Well, pop if pop has a problem, it will still return the garbage value that it got.
So your point is right, like this close to being absolutely right. So the reason why we don't want to combine pop, as you said, to be both an accessor and a mutator, has to do with the exception safety issue we were just talking about. So the problem is as follows. If we have top or pop both remove something and return it, then what happens in the situation where we make a copy of this guy? Okay, so we've decremented top by 1. So top, we've just lost the top item of the stack. That guy's gone, right? And then we think we're going to go ahead and assign this thing over to here, but there's an exception that's thrown at this point in the program. What will happen? Well, what will happen is you won't get back the item you were popping. That'll be lost, but the stack will be modified. So you won't have preserved the exception safety guarantees because you will have left the stack, you will have lost the value, and you can't get it back at that point. So that's a bad interface. Anytime you lose something and there's no way to stop it from being lost, that's a problem. So the issue here is by splitting these things into two operations, top will give you back the old value. And if that throws an exception, that's okay. You haven't perturbed the original stack at all. Nothing's been modified. If it gives you back the item, you're fine. You've got it. Pop will just take it off the stack. It'll remove it, but it won't try to return anything. So if it fails, it can be set up in a way where you don't actually modify the stack either. So if pop fails, you can preserve the stack as it was before and just not have anything happen as a side effect. So that's the reason why we don't want to munge those two things together. So that's a real good question. And this example is trying to be too clever in combining the two, but it won't be exception safe. Questions about that? That's a very subtle issue, and Jerry, Dr. Roth, was great to bring that up in 201 because it's much better to learn about it there, and then we can kind of take it on faith there and know sort of this rule of thumb, don't mix accessors and mutators. And then in 251, we can talk a little bit more in detail about why it works that way. Okay, another interesting thing you can do, I mentioned before, mostly you use templates or parameterized types to generalize over type, but you can also use them to generalize over constant. So here's an example of a stack, and I probably should change the name of this thing to fixed stack or something like that because it's not quite the same as the other one. In this case, notice we have two parameters. The type name, stack of T, int, double, employee record, activation record, whatever. And then size T, size, which is an unsigned value. So in that particular case, we can now allocate ourselves stacks of ints of, say, size 200 or 100 or 300 or whatever, right? You can select that. And one of the nice things about this is, unlike the other examples we've seen so far, this one doesn't use dynamic memory allocation. It uses static memory allocation. Now, why would that matter? Why would anybody ever want to use static memory allocation instead of dynamic memory allocation? Can anybody think of why you'd ever do that?
You're working in like a time-constrained environment for like real-time deadlines.
Great observation. So the observation was if you're working in an embedded system or a real-time system where you want to have the behavior both in time and space be as deterministic as possible, because you want to make sure things meet their deadline. You want to make sure that they don't run out of space unexpectedly. Then dynamic memory allocation becomes a problem because it's not always clear how long it'll take. You might try to allocate stuff and then you fail. It will take a variable amount of time to run because of the way that people implement heaps and free stores and so on. So in that particular case, it's usually a good idea to try to keep it deterministic. So this is a way of getting generalization. You don't hard code the size of the stack, but you don't also require the use of dynamic memory allocation. So just another design pattern, design principle you can apply. Questions, comments?
Actually, never mind. That's fine.
Okay. Any other questions about that? All right. So that's the end of the templates discussion. Now, lest you think that we're done with templates, we are not done with templates by any means. After we're done with this set of slides, the introduction to C++ slides, we're going to have a whole couple weeks on C++ standard template library. And you'll get a lot out of that, I hope. Let's see, trying to think. I'm going to show you something else interesting as we transition from one thing to the next. See if this is still on my Facebook page where I posted it earlier, hopefully. There we go. So you should look up in Forbes magazine. Hopefully everybody in Vanderbilt's reading Forbes magazine since you were young. There's an interesting article about, are there too many students going into computer science? And the answer at one level is absolutely not. If you take a look at the number of programming jobs or jobs that require knowledge of computing and software and algorithms and all the things we do about in our computational ways in this field, there is nowhere near enough supply of students to meet demand of people who want to hire our students. It's always remarkable. I should just point this out. Every fall and every spring there's a career fair that we have here. I think ours is coming up in February. I'll send you some more announcements to that to Piazza later. Make sure you try to go, even if you're not ready to, anywhere near getting ready to graduate and get a real job. It's just a good experience to go there and find out what employers are looking for and stuff. These days, we regularly fill them up with all the employers that will fit in the hall, and they are desperate for our students because it's such a demanding, there's so much demand for this. But the point is not so much that there's too many students for the demand. It's that a lot of people they're not necessarily in the major for the right reasons, I guess is the best way to put it. And that's the trickier issue. So not everybody has to be a computer scientist in order to be able to be successful, but having an awareness of computation and software and design and patterns and all the good stuff we're going to talk about is very essential at helping you, whatever you happen to do. So you might want to take a look. It's an interesting article. Some of the things I think are kind of funny. You definitely see this. It says, you'll always hear people in other fields express their sour grapes feeling about how CS is not deep enough or does not deserve all the attention. And you will find that throughout your life. It's actually sort of annoying at some level. So wherever you go, people will always be trying to tell you, pick your favorite old school topic in engineering. Plastics, that's really where it's at, This computer stuff, it's just a bunch of gobbledygook. I was talking to a guy in the government not too long ago who had a very important job. And we were trying to convince this guy that software was different from other forms of technology for what he was trying to apply it to. And maybe we should treat it differently and think about it differently because it was so expensive and we're spending an enormous amount of money on a lot of things you hear about these days that are very expensive and not working with software, right? And he was like, I don't know what the big deal is. Why do people always say software is special? It's not special at all. It's just like everything else. We shouldn't give it any other attention. And then finally I said, sir, you do realize that every major software-intensive project is way over budget, way late, and doesn't work. And you're saying we shouldn't treat it special. Why? Maybe the reason why it's over budget, late, and too expensive is because people don't understand what they're doing, which is actually the case. So maybe we should actually think about this. But it's just funny. People have this sort of old school mentality. And you'll fight that your whole life if you stay in this field. Until people with computational perspectives have two things happen. Number one, they get old enough to get to senior management positions. And number one, they acquire enough social skills to be successful in senior management positions. I'm not sure which one of those is harder, right? Okay, so the next topic up here is really where C++ got its start. So C++, does anybody here know the original name of C++? What was the original name?
C with classes?
C with classes, that's right. That was the original name that Bjorn Strustrup did back in the late 70s, early 80s when he was first doing this at Bell Labs. And he was really inspired by earlier languages like Simula 67, which had some of the concepts of virtual functions and so on and so forth. And so object-oriented programming was the first major paradigm that C++ supported. It's since gone on to do a lot of other things. You will still find object-oriented programming important, but it's becoming diminishing in terms of its role because templates and generic programming have taken over. But it's still helpful to understand how it works, and there's still lots of opportunities where you get to use it, and it works out quite nicely. So if you take a look at what we looked at so far up to this point, there are a couple of issues. Number one, if we wanted to make any changes to our existing solution, we wanted to change the implementation of any of this stuff, then using the techniques we've talked about up to this point, any changes we would have would require changing the implementation and then recompiling and relinking the code. So that might take a long time, and if you didn't have source code for some things, it might be impossible in some cases. And it'll also require access to the original source code. You have to go in there and modify the code. So you may not have access, people might not want to give you their code, it might be a long time to recompile everything, subtle inconsistencies can sneak in with respect to differences between the object code and the source code, all kinds of bad things can happen if that occurs. So if that is the problem that you're facing, where things are changing and you're breaking what you've already got, then you might want to apply object-oriented programming solutions to help you out with your problem. So what we would do here is we would use something called inheritance, which you'll quickly learn about, and dynamic binding. When those things are used together, they're very powerful. It's possible to do them without each other. You can have dynamic binding in C and C++ by using pointers to functions. You can use inheritance in C++ without using dynamic binding. STL does that in a few places. But like so many things in life, like Reese's peanut butter cups, the chocolate and the peanut butter put together are perhaps more tasty than either one of them by themselves. I had kale today for lunch. And by itself, it's probably not very tasty, but when you mix it up with an omelet, it tastes pretty good. Same thing is probably true for grits. Right? Grits by themselves, not so tasty. Put a lot of butter on almost anything and it tastes good, right? So, you can tell we're in the South. So this requires the use of C++ abstract base classes. So here's an example of an abstract base class, and we'll keep with our stack theme. By the way, the reason I chose to use stack for everything was that way we wouldn't have to keep talking about the particular details of the example. We could just keep changing the paradigm we're using to express it. Real examples are a lot more interesting than stacks. So here we're going to have a stack that's parameterized by type T, except now you can see it's a little different. In particular, you'll see that most of the methods are not implemented at all, but instead they're defined as two things: virtual, which is that keyword that appears on the left, and at the end of many, but not all methods, the word, or the symbol equals 0 appears. So virtual methods are dynamically bound methods, and that means they're selected at runtime based on the type of the object that's being invoked. And pure virtual methods, which is what equals 0 are methods that are not necessarily defined in the base class or some derived class, but they're obligations that must be eventually defined by some subclass before you can instantiate an object of that type. Now that's a lot of things to try to grasp at once, and we'll go through it a bit at a time. So the main thing to think about when you use virtual methods, you're saying to the people who are coming after you, the people who are developing other things that build off of what you've done, which could be yourself in 25 minutes, right after you define the base class, you're saying there are some obligations that have to be filled in, or there's some opportunities for customization here. A virtual function is basically saying there's an opportunity for customization. I'm going to define the interface, but I'm not going to dictate that this implementation must be the only implementation now and forever. That's what a virtual method means. A pure virtual method says, I'm going to obligate, it's not just an opportunity for extension, I'm going to obligate the people developing the subclasses that they must override these methods eventually and fill them in so that something happens that is meaningful at the level of abstraction that they are working, which again is a rather vague thing to say, and I'll quickly give you some meat to that discussion. But before I do that, any questions about the overall concept?
Well, just syntactically, equals 0 means pure virtual.
Assuming you have the word virtual before the method, equals 0 at the end of the method means pure virtual. If you don't have the word virtual ahead of it, and it's not inherited from a base class that has virtual for that method type, then it's a syntax error. But virtual equals 0 is a pure virtual method. That's right.
So the reason, excuse me, the fact that it can be selected at runtime is the reason why you don't have to recompile this entire class again.
Well, so the point was the fact that you can recompile things or the fact that you can override and select at runtime is reason you don't have to recompile. That's basically the case, because we're going to be able to use some really cool magic called virtual tables. They're going to be able to use runtime type information to dispatch the appropriate method to call. And so the way that this all works, I'll show you a little snippet of this later. When you write the code, it gets compiled in such a way that the determination of what method gets called is done at runtime by looking up in a table of pointers to functions. That's getting ahead of ourselves, but we'll get to that shortly. Question?
Oh, well, I was just going to clarify. So if you leave off the equal 0, then later users don't necessarily have to define that function.
Great question. So if we leave off the equals 0, then we have to provide an implementation, and that will be used by default. And later developers have the opportunity to subclass and specialize. If we put equals 0, you can also provide an implementation, but you are obliging someone later to define one as well. So it's really, mandatory versus advisory, if you will.
So is it like an abstract Java class where if it has one abstract method, you can't instantiate it?
That's right. So because in Java came after C++, and people were less concerned about donating their bodily parts to the language. So rather than C++, where they were coming up with cockamamie equals 0 weird syntax, right? The Java folks said, let's call the keyword abstract. We'll put it in the language to start with, and we'll use abstract. You can have an abstract class or an abstract method. A pure virtual method is like an abstract method in Java. Basically the same thing. Yes?
So like in this implementation, top is not a virtual method. Does that mean that any derived classes are not able to define their own top method?
Great question. So you'll see top, if you look here, top is not a virtual method. And I just did this to illustrate the point. I wouldn't necessarily do it this way in practice. This is actually something called a template method. We'll talk about this pattern in more detail later. I'm going to show you what it looks like in this slide. The top, if you take a look here, you'll see that its top is implemented by calling pop followed by push, which, by the way, is not the best way to do this, but I'm just showing you the point. So that's an example where we don't have to make top be virtual, but push and pop are virtual, so we can change those things. And so that's what's called a template method. You fix the order of the steps, but you leave open what the steps do. So that's what template method is. So I'm just illustrating that point. But your original point, which is the right one, hey, Jared, original point is that I can't redefine top because it's not virtual. But I could redefine push and pop, get the same effect. Other questions? Yeah.
So even though it's a public method, if you had a derived class, your top is just off limits entirely?
Top, so the question was, even though top is public, if you derive from it, it's fixed. So literally what will happen here, non-virtual methods, when they are eventually compiled into code, turn out to be method calls directly. They're embedded into the object code. You'll be a call to that method. Virtual methods, in contrast, as we'll see shortly, aren't embedded into the object code directly. Instead, you indirect through a pointer to a table of functions, through an index, and so they're dynamically bound. That's the fancy term. So that's the main difference. Other questions? Okay, so we're probably not going to get through all of this stuff, but let me show you where we're headed. Where we're headed with this stuff is we're going to have different implementations of stack. I'm going to go through this in lightning speed, and then we'll come back later in next Wednesday and cover it in more detail. So we're going to make a vector stack, and we're going to make a linked list implementation of a stack. As you guys all know, hopefully from 201, there are different ways to implement a stack. So we're going to have one that inherits the stack interface, overrides these methods, doesn't fix the problem with pop, which we talked about before, and we use an STL vector here. And then we're also going to have a linked list implementation of stack, which has the same interface, but the implementation uses a linked list, not a vector. And we'll talk about how to do that stuff as well. And where we're headed with all this, just to give you the forest view rather than the tree view, is we can now write functions like this. Here's a function called print top, which takes a pointer to a stack and it says stack arrow top. And when you call, print top, what this thing will do is essentially it's going to take the stack pointer, go find something called a v pointer for a virtual pointer, which points to a virtual table, which is an array of pointers to functions. It'll index to the right one based on the method that you called, push being number one. It'll then find a pointer to a function there. It'll call that pointer to a function, passing in the stack pointer and whatever parameter you have to pass to that thing. So what happens there is that call is dynamically bound. And so you can change what's passed in to print top. You can pass in a stack that's a v stack or a vector stack or a list stack, an L stack. And this code never has to change, but we can change the implementation arbitrarily to do lots and lots of different things. So that's kind of where we're headed with all this stuff. So as we were saying before, unlike the original version where you have to go back and change the implementation and then recompile all the client code, by using object-oriented programming, you can write a piece of code once, like print top, give it a pointer or a reference to a base object, and then you can pass it in derived objects till the cows come home, and you can keep adding those things ad nauseum, and all kinds of cool stuff happens.